Okay, so you know that scene from Psycho? Marion is in the shower, indulging, thinking she is safe now, but then all of a sudden you hear those violins shrieking. And in that moment, you are right there with her, feeling her pain as she gets stabbed. Today, we will explore how music taps into our bodies and brains to generate empathic responses, connecting us to the character's own emotions. From gestures and postures to timbre and harmony, we'll break down the science of musical empathy and the role of the mirror neuron system. And along the way, we will watch a series of compelling film scenes that show these ideas in action. This figure places empathy alongside other developments from cognitive semiotics. As we can observe, the formalized study of empathy did not emerge until recently, and this figure places empathy within a bigger picture of how we make sense of film music, placing it as the one mechanism closer to gut-level perception and arguably the most distant to the analytical or intellectual ones. But remember, as mentioned earlier, although these layers work together, not separately, for the sake of clarity, we break them down one at a time. Before we dive into these ideas, I want to highlight that Juan Chata explores them in greater depth, with additional examples in his book Film Music: Cognition to Interpretation. His research does not just explore how sound and image interact, it also unpacks what happens inside our brains when we process these connections. If you have ever wondered why a musical cue can instantly transport you to a time, place, or emotional state, his book offers some eye-opening insights into the cognitive and perceptual machinery behind it. First things first, let's talk about interpersonal empathy before we throw music into the mix. Empathy isn't just a surface reaction, it's deeply wired into our brains. When we see someone's emotions or actions, our brain lights up in the same way as if we were feeling or doing the same thing. This is thanks to the mirror neuron system, which forms the biological backbone of our ability to empathize. In a snapshot, empathy functions as follows. A physiological state modulates an individual's affective states and influences their vocal and bodily gestures and postures. Through a mirroring system, we simulate those vocal and bodily gestures and postures, which prompts us to experience an analogous affective state. But let's parse out these steps in more detail. We begin with the encoding of emotion. We uncritically accept the idea that emotions trigger physiological states, that our mood defines how we feel physically. However, much research in cognitive psychology indicates that this belief stems from intuitive yet misleading sensory information and suggests that the reverse chronological relationship is at play. Physiological states cause emotions. William James was one of the earliest psychologists to advance this counterintuitive proposition when he writes, "Common sense says we lose our fortune, are sorry and weep. We meet a bear, are frightened and run. We are insulted by a rival, are angry and strike. This order of sequence is incorrect. The bodily manifestations must first be interposed. The more rational statement is that we feel sorry because we cry, angry because we strike, afraid because we tremble. We extemporize our physiological and affective states through gestures and postures. But there's a subtle distinction here. A gesture is something you do, a wave, a shrug, a nod. It involves movement. A posture, on the other hand, is something you hold, the way you're standing, the way your shoulders slump when you're tired or tense. It's more static, but still very much alive in terms of expression. Both Gestures and postures are constantly sending out emotional signals. They're like these little ambient broadcasts of how we're doing on the inside. And the interesting thing is that most of it happens below the level of conscious awareness. That's why a glance can feel completely different depending on how it's given. A quick flick of the eyes might be neutral, but add a little tension, change the pace, and suddenly it becomes a flirt or a challenge. Since we will talk about subvocalization today, let's think about the human voice, which is not just as a tool for language, but as a full-blown emotional instrument. It's not just what we say, it's how we say it. The pitch, the rhythm, the texture of our voice, it all carries emotional weight. These very qualities shape and transform meaningless sounds into meaningful sonic gestures. A mere exhalation becomes a lamenting sigh or a disgruntled moan. Researchers call these qualities acoustic signatures. They're like emotional fingerprints embedded in our vocal gestures. But how do these acoustic signatures come about? Physiological changes not only affect our self-perception of emotions, but also modulate our vocal expressions. They impact respiration patterns, degrees of salivation, muscular tension, subglottal pressure, transglottal airflow, vocal fold vibration, and many other phenomena that affect our phonation and articulation, embedding acoustic signatures within our vocalizations. Scientists have actually studied these acoustic signatures, things like pitch, loudness, how much the sound vibrates, how quickly syllables start. What they've found is fascinating. Different emotions tend to have distinct acoustic profiles. In other words, anger sounds a certain way, while sadness sounds in a different way. For example, angry speech tends to be louder, more forceful, with sharp changes in pitch, almost like it's bursting out. Sad speech, on the other hand, is often quieter, flatter, slower. So what we are really seeing here is this close link between how we feel and how our bodies physically produce sound. But there is one other component here. Acoustic signatures appear to have an ecological, albeit expressive, function, providing members of the same species, and other species as well, with critical and behaviorally relevant information. Eugene Morton explored vocalizations in a wide range of species. When animals interact, their behaviors can be classified as either hostile or friendly. He found a pervasive pattern where low pitch and loud volume vocalizations are associated with aggressive behaviors. In contrast, high pitch and soft volume vocalizations are associated with submissive or friendly behaviors. He suggests this stems from an adaptive mechanism. When animals need to create threatening displays, for example, they behave in ways that tend to make them appear larger. The larger, the more threatening. Because a sound is a direct indicator of the source's size, it does the trick in altering the perception of their actual size. More recently, in Universals of Human Language, Bollinger observed the same patterns of behavior in humans. Vocalizations in the low frequencies and with louder volumes denote aggressive and threatening behaviors, and vocalizations in the high frequencies with softer volumes denote submissive or friendly behaviors. Which brings us back to the model for empathy, and to its most significant ingredient, the mirroring mechanism that underpins empathy. This is thanks to the mirror neuron system, which allows us to simulate the vocal and bodily gestures and postures of others. Let's briefly review the mirror neuron system. About 30 years ago, scientists found a new kind of motor neurons in monkeys. These neurons fired both when the monkey performed an action and when the animal saw someone else doing that same action. These neurons, now called mirror neurons, were a game changer in understanding how we connect with others. Then, in 2002, researchers discovered audio-visual mirror neurons, which activate when monkeys either perform an action or hear the sound associated with it. Essentially, these neurons translate what we see or hear into our motor system, bridging the gap between perception and action. Although mirror neurons were first found in monkeys, non-invasive techniques like fMRI and TMS have shown that humans have a similar system. So now let's cover the last step in the model, the decoding of emotions. Jaby and Keezer's 2008 found that observing emotions in others' facial expressions causes a sequential two-part response in the brain. First, we activate the cortical motor activity responsible for acting out those facial expressions. Subsequently, we engage the neural substrate responsible for processing feelings and emotions, the insula. So when we see others' postures or gestures, we mimic those postures or gestures internally, which causes us to feel the same way they are feeling. In fact, and I take a detour here, this mechanism helps us self-regulate our own emotions. Kieser's 2011 points us to research suggesting that changing our own facial expressions, lowering our eyebrows, clenching our jaws, raising our mouth corners, helps us modulate our own affective states. So our emotional states, how we feel, are tied directly to what our bodies are doing. If you assume a posture, let's say you force yourself to smile, even if you don't feel particularly joyful, your body kicks off a chain reaction. Your heart rate shifts, your skin starts responding, and suddenly your brain starts going, I guess we're happy now? There is much research supporting this. Levinson and colleagues found that the difference between a real smile and a fake one is not that big. Both trigger similar responses in the brain. Same with other expressions: fear, anger, surprise. This confirms that your posture, your expressions, they're not just reflections of how you feel. Sometimes they're the cause. So to sum up, a physiological state modulates our affective states and influences our vocal bodily gestures and postures. Through a mirroring system, others simulate those vocal bodily gestures and postures, which prompts them to experience an analogous affective state. Now that we have a strong hold of the model for empathy and its various mechanisms, let's translate this to our empathic responses to music. First, composers interweave musical gestures in the score, which function as correlates of vocal and bodily gestures. When listening to the music, audience members mirror these musical gestures via three sub-mechanisms: subvocalization, entrainment, and contagion. And the physiological responses stemming from this internal simulation elicit in the audience the composer's intended affective state. Just like with interpersonal empathy, let's parse out the encoding process. Remember Morton's study in vocalization in mammals, which we mentioned in interpersonal empathy. Now, Huron, Kinney, and Pricoda extended these findings to music and found the same relationship. In their study, listeners judged a melody in the low register with loud volume as denoting aggression or threat, and the same melody in the high register and soft volume as denoting friendliness. This table summarizes their theory, the acoustic ethological model. Their findings directly apply to music composition to elicit specific affective states. Drawing on these findings, I composed snippets of music, or just sounds, to elicit distinct affective states. For example, for aggression, seriousness, or threat; for friendliness or appeasement; for sadness, relaxation, or sleepiness; and for fear or alarm. Of course, some echoes of Psycho there. Huron and Pricoda only looked at two parameters: pitch frequency and volume. But music comprises many parameters, including contour, pitch collections, rhythm, tempo, timbre, density, meter, harmonic movement, degrees of consonance and dissonance, and many more. Although many of these parameters have been studied individually to understand their ability to evoke emotional states, they are rarely examined in combination. Additionally, most existing research focuses on parameters traditionally analyzed in music theory, overlooking parameters that may be even more influential in eliciting affective responses, such as spectral components, reverb, sound placement and movement, sounds envelope, compression, and more. So far we have explored, albeit briefly, how composers encode their intended physiological and affective states into the soundtrack through musical gestures. Then, when we listen to the music, our mirror neuron system activates via three sub-mechanisms: subvocalization, entrainment, and contagion. Today, we only focus on subvocalization. Subvocalization is when we internally mimic vocal sounds, like language, laughter, or screams. It's fascinating because when we do this, our brain uses the same pathways as if we were making those sounds. This process lets us experience the emotions tied to those sounds firsthand. Researchers have explored this idea a step further, suggesting that this mirroring process doesn't just happen with vocal sounds, it works with instrumental sounds too. And here is where we complete the mechanism of musical empathy. As we mimic the external sounds and our physiology adjusts accordingly, our affective states change. Film composers know or intuit this and use it to their advantage, constructing soundtracks that help us internalize the emotions of the characters on screen. The human voice plays a pivotal role in Gladiator's musical score, prompting us to empathize with the protagonist's affective states by engaging our mirror neuron system via subvocalization. In this scene, Maximus arrives at his worst nightmare: vineyards destroyed, earth scorched, houses smoldering. As he collapses off the horse, in the soundtrack we hear a solo vocal lament over a low drone. Here, the solo voice texture reflects the intimate grief of an inner psychological space. The timbre of closed-mouth vocalizations conveys a suppressed emotion, and the melodic contour suggests the visceral representation of an animal lament. While listening to the music, we subliminally engage our mirror neuron system through subvocalization, which compels us to mimic those sounds in our own vocal apparatus and thus resonate with Maximus's suffering. As we mentioned a few moments ago, the mirroring process of subvocalization doesn't just happen with vocal sounds, it works with instrumental sounds too. Two examples from 15 minutes nicely exemplify how the music maps the character's bodily and vocal gestures onto instrumental ones. In this early scene, Emil violently lashes out after discovering that his old partner has squandered their stolen money. The camera follows him as he moves erratically, sobbing, pacing, and ransacking the apartment. The score doesn't simply accompany the chaos, it mirrors it. The violin part unfolds in jagged, angular bursts. Abrupt attacks, unpredictable leaps, abrasive textures. These musical gestures closely track Emil's physical ones, mapping his movement and emotional disarray into the music via acoustic signatures characteristic of anger. Through this tight correspondence between musical and bodily gesture, the score engages us viscerally. The music not only prompts us to emulate his fury, but to feel it firsthand.
Fucking God! Itu sasaran harus lagi. What are you looking for, huh? What are you looking for? Bohemian barbecue.
Near the end of the film, Oleg lies fatally wounded, still gripping his camera. In a final, surreal act, he films his own death, slowly panning from the Statue of Liberty to a close-up of himself as he dies. The music enters quietly, a solo violin tracing a smooth, restrained line. In fact, this is the same motivic idea from earlier in the film, but now it is stripped of energy, softened, and mournful. Its shape maps Oleg's fading gestures. Gentle, narrow in range, rhythmically stable, harmonically subdued. These acoustic signatures prompt us to bodily mimic these gestures, guiding us toward empathizing with Oleg's final moments.
Hey, boss! He's still alive!
Come on, let's go.
The film by Oleg Krasgul. How was that? That was great.
Among the many acoustic signatures, timbre is arguably the most efficient in triggering an effective response. While subvocalizing those timbres, we subliminally adapt our vocal apparatus to almost perform them. Our ability to perceive and imitate timbres using our own vocal system is closely tied to how a sound's harmonics, also called overtones, interact. These interactions shape how consonant or dissonant a sound feels to us on a sensory level. So let's take a moment to break that down, what we mean by harmonics or overtones. When we hear a musical note, we're not just hearing a single frequency. What we call a note is actually made up of many frequencies layered together. The lowest and strongest of these is called the fundamental, which determines the pitch we perceive. But above that fundamental are additional frequencies called harmonics or overtones. These are higher frequency vibrations that occur at whole number multiples of the fundamental. So if the fundamental is vibrating at 110 hertz, the first harmonic would be at 220 hertz, the next at 330 hertz, and so on. Take pure tones, for example. These are sounds with a strong, clear fundamental frequency and only a few simple overtones, usually just the second or third harmonic. As a result, there's little friction between frequencies, which means they're easy for our vocal system to reproduce. They don't require much tension in the vocal folds and feel smooth or clean to imitate. Now contrast that with noisier, more complex sounds like a harsh buzz or a scream. These tones have a weaker or less prominent fundamental and contain many inharmonic partials, meaning the overtones don't align neatly with the harmonic series. The clashing frequencies create a kind of acoustic friction, what we hear as sensory dissonance or noise. To emulate these rougher timbres with our own voice, we instinctively apply more muscular tension, especially in the vocal cords, because reproducing those complex textures physically feels dissonant. In other words, our body recognizes the tension in the sound and mirrors it. This spectrograph shows the same pitch, middle C, C4, played on 4 different timbres: a sine wave, a flute, a trumpet, and a distorted electric guitar. Bright yellow regions indicate where the sound's energy is most concentrated. These are the frequencies we hear most prominently. At the top, the sine wave displays a single clean band. This indicates the absence of inharmonic partials, which are frequency components that do not align with whole number multiples of the fundamental. The result is a pure tone, often described as bland or hollow. Next, the flute shows a small number of additional bands, representing a few overtones. These contribute to the flute's characteristic timbre, which listeners often describe as smooth, warm, or mellow. In contrast, the trumpet has a much denser spectrum. The presence of numerous partials, including many higher frequency components, gives the trumpet its bright, piercing, and incisive quality. Finally, the distorted guitar shows energy spread across nearly the entire spectral range. This dense array of inharmonic partials results in a noisy, gritty, or harsh timbre. The takeaway is this: the presence and intensity of inharmonic partials significantly shape how we perceive a timbre, but they also influence our embodied response to it, and hence we associate smoother timbres with sadness or tenderness, while we associate rougher or brighter timbres with anger or excitement. Film composers are highly attuned to the emotional power of timbre. They deliberately select specific instrumental colors to shape the listener's emotional response, particularly when orchestrating musical gestures. In 15 minutes, we heard 2 contrasting uses of the violin. Though the instrument remained the same, the performance techniques differ dramatically, producing 2 distinct timbres, and with them, 2 distinct emotional effects. In the first example, the sound is sharp and spectrally dense. It contains a high concentration of inharmonic partials, contributing to a sense of psychological tension or distress.
What are you looking for, huh? What are you looking for? Oh, no! Bohemian barbecue.
In contrast, the second example features a much smoother timbre with fewer inharmonic partials. This produces a more subdued, sorrowful atmosphere. Which brings us to the example from Psycho that opened this session, where a violin takes on an extremely rough timbre. Subvocalizing a scream or a sound that resembles one is physically uncomfortable. Screams require tension in the vocal folds and produce a flood of inharmonic partials. And this is exactly what happens in Psycho's shower scene. As we are peacefully indulging in the white noise of the shower, the sudden violin's high-pitched, strident acciaccaturas mimic the harshness of a scream, both in texture and intensity. As listeners, we subconsciously mirror those gestures, and in doing so, we don't just hear Marion's pain, we feel it. While instruments like the violin, as we heard in the foregoing examples, offer a wide spectrum of timbral variation depending on how they're played, others have a more consistent sound profile. These more stable timbres often become closely associated with particular affective states in film scoring, serving as reliable tools for shaping affect. The French horn is known for its smooth, warm tone. It has few inharmonic partials, a strong fundamental and focused energy in the mid-range. These features give it a sense of calm strength. As a result, it's often associated with nobility, sincerity, and emotional resolve. The oboe, by contrast, has a more nasal quality. Its sound contains rich odd harmonics and a strong mid-frequency presence. This gives it a plaintive, expressive tone, often linked to sadness, introspection, or emotional vulnerability. Timpani sit on the opposite end of the spectrum. They produce strong low-frequency fundamentals, minimal inharmonics, and a deep, sustained rumble. These qualities give timpani their sense of weight, tension, and looming threat. Muted Muted trumpets, especially with Harman or cup mutes, produce a filtered timbre with narrow frequency content. They emphasize the upper mid-range while suppressing the low end. This creates a tone that feels constrained, almost pinched, perfect for expressing unease, irony, or anxiety. It is a timbre made famous in noir and espionage scoring. Celestas occupy the upper end of the spectrum. Their sound is light, percussive, and bell-like, high in frequency content, quick in attack, and nearly free of inharmonic overtones. This creates an immediate sense of innocence, wonder, or magical curiosity. So it's no surprise they feature prominently in fantasy films and scenes involving children or discovery. Lastly, the contrabass, not when plucked but played with the arco, offers a dense, resonant sound full of low frequencies and complex overtone content. With its slow onset and shadowy tone, it evokes foreboding and dread. Today, we only cover a few representative examples of the French horn. In Jurassic World: Fallen Kingdom, the score uses the French horn to project nobility and loyalty onto a dinosaur, specifically Blue. The horn's timbre, warm, rounded, and low in inharmonic partials, matches the acoustic profile often associated with honor and emotional sincerity. As Blue stands outside the Lockwood mansion, the horn plays a gentle, centered melody, reinforcing her perceived trustworthiness. By embedding these acoustic signatures, the score prompts an empathic response, encouraging us to view Blue not simply as an animal, but as a sentient, moral being.
Hey, girl.
Owen.
It's okay. She won't hurt us. Blue, come with me. We'll take you to a safe place, okay?
In this scene from Disaster Movie, a character announces his intent to act honorably. As he does, a French horn enters the score. Again, the instrument's rich, warm timbre, low in inharmonic partials and high in tonal clarity, immediately signals nobility, sincerity, and honor. By aligning this musical timbre with the character's declaration, the score invites us to empathize with his intentions. We don't just understand that he's doing something noble, we subliminally feel it.
We gotta go back.
Say what?
Amy's in trouble, man. I'm going back for her. I let her go before. I'm not losing her again.
Yo, man, now you crazy, man. It's all kind of shit breaking out in the city. We don't leave right now, we're gonna die.
Something I gotta do. You guys keep going.
Nah, I'm your boy, man. I'm gonna roll with you.
Yeah, I mean, I'm already knocked up, so what other shenanigans can I really get into?
At the close of this X-Men scene, a character makes a quiet but resolute choice, one that signals emotional restraint and moral clarity. The score responds not with grandeur but with subtlety. A French horn-like timbre enters, mirroring the tone of dignified resolve. Notice that it is a sound closely resembling the French horn, but does not seem to be the natural acoustic French horn. This complicates the message slightly. It evokes the effective resonance of an acoustic horn, but also hints at the artificial or augmented nature of the characters themselves. Still, the emotional cue is clear. The timbral qualities, smooth contour, centered register, and subdued overtones, elicit a clear empathic response, inviting us to resonate with the character's choice as both human and honorable.
This is our life.
Here, we embark on the last extension of our theory of empathic responses via subvocalization to explain our responses to consonant or dissonant sonorities. In a nutshell, we respond to harmonic dissonance in chordal constructs in much the same way as we do to sensory dissonance in timbre. This argument, although not tested empirically, rests on a perceptually grounded premise. Both involve acoustic roughness or instability, and both evoke visceral affective responses. In both cases, timbre and harmonic constructs, it's about how sound waves interact and how that interaction affects our bodies. This analogy is appealing because it suggests a unifying mechanism, one that aligns with subvocalization and embodied empathy models. Just as our bodies instinctively tense up in response to noisy, abrasive timbres, so too might they respond to harmonically dissonant chords with a similar physiological mirroring: tightened muscles, shallower breath, heightened arousal. So in broad terms, consonant harmonies often evoke stability, calm, or resolution. Dissonant harmonies often evoke instability, urgency, or conflict. Of course, film composers use this to great effect. By manipulating chordal consonants and dissonance, they shape our emotional experience of a scene. Because they are rather static, I see harmonic constructs or chords as akin to musical postures rather than gestures, because there is no inherent movement or progression. This scene from Jurassic World: Fallen Kingdom offers a representative example, highlighting how harmonic language can mirror and prompt emotional shifts. Here, a young character clings to a rescue ladder dangling from a helicopter with a dinosaur in pursuit. As the dinosaur grabs onto the same ladder, the situation becomes precarious. At this point, the score saturates the moment with dissonant harmonic constructs, clashing sonorities that amplify the suspense and instability of the action. When the dinosaur unexpectedly lets go and the character escapes, the music abruptly shifts to consonants. Major triads emerge, reflecting a sense of relief and triumph. But that relief is short-lived. Within seconds, a massive sea creature erupts from the water and devours the character. The music plunges back into sharp dissonance, underscoring the sudden reversal and emotional shock. Here, harmonic constructs do more than accompany the action. They shape our emotional arc as viewers, intensifying tension, release, and devastation in perfect synchrony with the story. We covered quite a lot today. from the mirror neuron system to timbre, harmonic dissonance, and embodied responses to sound. And through the lens of film music, we saw how composers use these tools to draw us in, to make us not just understand a character's experience, but feel it in our bodies. If this talk piqued your interest, you'll find a much deeper exploration of these ideas in Juan Chata's book, Film Music: Cognition to Interpretation, along with a companion YouTube channel that delves into many of the examples we covered today. I hope you'll check them out.